Hello guys, welcome to Dr. Science. So today our topic is about glomerular filtration rate. First we will draw a small diagram in order to understand this. So here is the efferent arteriole which will eventually end up into the capillaries, and the efferent arteriole. So here is the efferent arteriole, and this one is your capillaries, and finally into the efferent arteriole. And this one is your Bowman's capsule. Now this entire apparatus is called as your glomerulus. Now if there is 600 ml of plasma, this plasma is going from efferent to efferent arteriole. Out of this 600 ml, 120 ml will go into the glomerulus, and this plasma which is getting filtered, this plasma, the 120 ml which is getting filtered at the glomerulus, is called as your glomerulus filtration rate. I hope you understand the definition of glomerular filtration rate. Okay, now this glomerular filtration rate is dependent on certain factors. We have to understand that. So urine formation is dependent on the GFR. How we need to understand. So this is the Bowman's capsule, and eventually the Bowman's capsule will lead to formation of urine. So this urine formation is dependent, on the cofactors such as the GFR and other factors. So first we will see, here is the efferent arteriole, here are the capillaries, and here is your efferent arteriole. I already told you, whenever the plasma is flowing, it will get filtered into the glomerulus. So the first component is the GFR, glomerular filtration rate. Now in the proximal convoluted tubule, there are certain cells which will absorb certain substances, especially glucose, sodium, amino acids, which is needed for our body in cellular metabolism, and this is called as your tubular reabsorption. What is meant by tubular reabsorption? Whenever the plasma is flowing, the plasma contains certain important factors such as your glucose, sodium and amino acids, which will get reabsorbed in the PCT. Obviously these substances are not found in the urine, hence in the equation GFR we have to minus the tubular reabsorption. Why we are removing tubular reabsorption? Because they are not found in the urine. The glucose, sodium and amino acids, they are not found in the urine. That's why we are removing the tubular reabsorption. So aside from that, certain toxins, so certain toxins are also present in our body, and we have to remove these toxins. How can we remove these toxins? By secreting them into the proximal convoluted tubule, and this is called as your tubular secretion. So in urine formation, we have the equation is GFR minus tubular reabsorption plus tubular secretion, because toxins will be excreted into the urine. That's why we are adding tubular secretion. So this is the equation of the urine formation. I hope you are clear with this. Now this GFR here is dependent on certain factors. So GFR is equals to net filtration rate, net filtration rate into filtration coefficient. Okay. Now what is this net filtration rate and filtration coefficient? First we will start talking about the net filtration rate. Net filtration rate, we have to talk about the factors which are favoring and factors which are opposing, but especially we will talk about the glomerular capillaries and the Bowman's capsule. So here is your efferent artery. Draw this diagram a little bit big, and these are your capillaries, and here is your efferent artery. So whenever the plasma is flowing from these arterioles, this plasma is getting pushed into the Bowman's capsule, and that plasma needs some pressure in order to escape from the capillaries. That pressure is called as your hydrostatic pressure. So hydrostatic pressure is nothing but the pressure which is required in order to plasma escape from the capillaries into the Bowman's capsule, and it is of 50 mmHg or 50 mmHg. Okay. Now if there is hydrostatic pressure there, obviously there should be oncotic pressure which will be opposing that one, right? So oncotic pressure is the pressure that is opposing the hydrostatic pressure, and this oncotic pressure is mainly dependent on proteins such as albumin. So what is the oncotic pressure that is opposing the hydrostatic pressure? That is nearly 30 mmHg. So we will denote the hydrostatic pressure by P, whereas we denote the oncotic pressure by pi. Since it is capillaries, we will write hydrostatic pressure, that is in glomerular capillaries, minus oncotic pressure, that is in glomerular capillaries, is equals to net filtration pressure in the glomerular capillaries. Just draw with this one. So net filtration pressure in glomerular capillaries is the hydrostatic pressure. How much was it? It was 50 mmHg minus the oncotic pressure in the glomerular capillaries, that was 30 mmHg. So what is the net filtration pressure in the glomerular capillaries? It is somewhere around 20 mmHg. So this is equation number 1. Now if there is hydrostatic and oncotic pressure in the glomerular capillaries, obviously there should be oncotic and hydrostatic pressure in the Bowman's capsules also, right? So this is the efferent and efferent arteriole. So there is hydrostatic and oncotic pressure in the Bowman's capsule also. Okay. So there is hydrostatic pressure. We will denote the hydrostatic pressure by P. What is the hydrostatic pressure that is present in the Bowman's capsule? I am not talking about the capillaries. We have hydrostatic pressure in the Bowman's capsule also. So the hydrostatic pressure that is present in the Bowman's capsule is 10 mmHg. We will denote this hydrostatic pressure by PB. P means hydrostatic pressure, and B means in the Bowman's capsule. Okay. And similarly, there is the force that is opposing the hydrostatic pressure, and this is your oncotic pressure, which is denoted by pi. So what is the oncotic pressure? Now oncotic pressure in the Bowman's capsule is 0 mm. Why is that? Because in the Bowman's capsule, in a healthy Bowman's capsule, there are no proteins, because there is a thick basement membrane between the capillaries and the Bowman's capsule. There is a thick basement membrane, and this basement membrane will not allow any proteins to leak into the Bowman's capsule. Hence there is no oncotic pressure in the Bowman's capsule. So the oncotic pressure is denoted by pi b. So in simple terms, what is the net filtration pressure in the Bowman's capsule? It is hydrostatic pressure Pb minus the oncotic pressure, which is pi b. So the net is 10 mm Hg. The net filtration pressure in the Bowman's capsule is 10 mm Hg. So we need to calculate the net filtration pressure, and we do this by subtracting the net filtration in glomerular capillaries and the net filtration in the Bowman's. In the glomerular capillaries, in the equation 1, as you can see here, it was 20 mm Hg. So we subtract 20 mm Hg minus, in the Bowman's capsule, this is the equation 2, we got 10 mm Hg. So 20 minus 10 is equals to 20 minus 10 is equals to, we get 10 mm Hg of the net filtration pressure. Let me draw this with a different color. So the net filtration pressure in total is 10 mm Hg. So GFR, glomerular filtration, is equals to net filtration pressure into filtration coefficient, and the net filtration pressure we obtained was 10 mm Hg. And what is this filtration coefficient? This filtration coefficient, we'll talk about this one here. Filtration coefficient. So filtration coefficient is nothing but how effectively is the plasma is filtered through this glomerulus. In order to understand this, it have two components. The filtration coefficient has two components: the hydroic conductivity and not only that, surface area. This filtration coefficient is dependent on two factors. One is hydroic conductivity, other one is your surface area. Now what is meant by hydroic conductivity? So here is efferent arteriole, capillaries, and the efferent arteriole. Now the net filtration pressure was 10 mm Hg. Now imagine I keep a pipe here, which is very narrow pipe. Do you think the permeability will be more or less? Obviously the permeability will be less. So the filtration coefficient also can be less. Similarly, if we take another glomerular or the efferent arteriole, I am going to take a big pipe here. The pipe is a very big pipe, and the net, okay, So that here is 10 mmHg, the net filtration pressure is 10 mmHg. If the pipe is bigger or wider, then obviously there will be increased permeability, right? If the pipe is wider than compared to the last one, there will be increased permeability. So we can say that the filtration coefficient is increased. Hydraulic conductivity is nothing but the permeability of it is the permeability. Hydraulic conductivity is nothing but the permeability. If there is a smaller or narrow pipe, there will be decreased flow. Whereas if we keep a long or a wide pipe, obviously there will be increased permeability. So that was about hydraulic conductivity. Next, we will talk about the surface area. So if this capillary is having a surface area of 10 mm, this is having a surface or area of 10 mm, obviously the surface area is less, so the permeability will be less. Now imagine a condition where the surface area is lot bigger. Here the surface area is about 100 mm. So what will happen? Obviously there are a lot more pipes, so there will be increased permeability. So filtration coefficient is dependent on two factors. One is hydraulic conductivity and the surface area. So whenever there is increased hydraulic conductivity or permeability, the flow will increase. Or if there is increased surface area, then also the flow will increase. The GFR will get increased. So in simple terms, we can say that GFR is directly proportional to net filtration pressure. If the net filtration pressure is going to increase from 10 mmHg to 20 mmHg, the GFR will also increase. Not only that, GFR is directly proportional to the filtration coefficient, because if there is increased permeability, obviously it can filter more, so GFR will be increased. Similarly, if there is increased surface area, then also there will be increased GFR. Can you name some condition where there is decreased permeability and decreased surface area? Conditions where there are decreased permeability is your diabetes mellitus and hypertension, because long-term complication of diabetes mellitus, that is after 10 or 15 years, the kidneys will get damaged and the permeability or the hydraulic conductivity will decrease, and this will lead to decreased permeability, and eventually the GFR will decrease. Similarly, in long-term hypertension people, the permeability will decrease and GFR also increase. And conditions where the surface area will decrease is pyelonephritis, infection of the kidney. This pyelonephritis will cause fibrotic changes in the kidneys, and this will cause a decrease in surface area. So obviously the filtration coefficient will decrease and GFR will also decrease. So that was about GFR. I will talk the remaining in my next video. Thank you guys.